This is Mr. Wise. Today we're going to be talking about magnetism and electromagnetism. If you look at the first slide in the first picture here, you will see a picture of a magnet. And one of the practical uses here is the maglev train. As far as I know, they're only used in Japan. Um, it, from what I understand, also they're pretty expensive, and otherwise they may have replaced other trains other way. Uh, in other parts of the world, because what they actually do is they levitate just above the track, so there's much less friction, and they can go almost as fast as an airplane, very fast, but on the ground. And you see the track there looks different, so it's a big expense in implementing it, but has a lot of wonders for that. And who knows, we might see something like that in the future. So magnetism is all around us and used in a variety of different things. The Earth is a magnet, and the first magnets were naturally discovered, and they were called lodestones, and they were found in a town in Greece called Magnesia, and that's where the word magnets comes from, is simply from the name of the town in Greece. The Chinese, ancient Chinese, would use the lodestones to navigate ships, kind of like we would use a compass today. They just didn't have it in the same format as what we did, but they used the compass. But the Earth is a magnet, and we have a magnetic field, and that magnetic field protects us from a number of things. But we have a South Pole and a North Pole. Now, the difference is that we have a geographic North Pole and a geographic South Pole. The magnetic North Pole and the magnetic South Pole are not at the exact same spot. And so a compass doesn't actually point to the North Pole. On a map, a good quality map that has the directions listed on it, there's actually 3 different norths that are listed on a map. And that would be grid north, which is the direction that the arrow or the compass rose in the map points to where north is. True north, which takes you to the North Pole, and then magnetic north. And depending upon where you are at in the world, that declination or difference between the magnetic north and the true north is something that if you're navigating with a compass and a map, you need to know what that declination is, so that as you convert from, say, the map to the compass or from the compass to the map, you can make your conversions in order to be the same. Some places, like around here in Pennsylvania, it might be 7 degrees, 8 degrees, 9 degrees, 10 degrees, 11 degrees, just depending on the latitude and the longitude of where we're at, as far as what that declination is. And any good map will tell you what that magnetic declination is going to be. So the magnetic poles are the regions of the magnet that produces the magnetic forces. And just like the law of electric charges, this is the law of electromagnetic charges. Like poles repel, opposite poles attract. And the thing is with the magnet is it's strongest at the poles. It says the poles are the region that produces the forces. So magnetic strength is strongest at the poles, not in the middle of the magnet. And we will see that in just a bit. The magnetic field is the space around a magnet in which its magnetic force is exerted, and the shape of its magnetic field is revealed by magnetic field lines. Now, you will see the drawing here of just one magnet. These are the magnetic field lines. I'm going to show you 2 videos here in just a minute, and they will help to demonstrate that as well. Opposites attract, so you'll see that those lines get connected in the opposite poles, whereas in the similar poles, there is that force of repulsion between the two, and the lines do not ever actually touch. So what I'm going to do is I'm going to jump screens here, and I'm going to play this video. I'm going to narrate it instead of using the talking that they have. But basically, in that petri dish, they had some iron filings, and real fine, almost a granular sand type size of iron filings, and they have a magnet there. And as he continues to spread out these iron filings, you can start to see the pattern of that magnetic field the same way it was just being drawn. You kind of just have to look at the way the orientation is. Notice that here in the middle of the magnet, it's kind of shaped, and here at the poles of the magnet, the shape of the field matches that drawing that we saw just a few moments ago in my notes. Now, that was just one magnet. Doesn't matter if this is north and that's south or south and north. It doesn't really matter because the effect is the same. In this particular video, we have 2 magnets, and they start with like poles together. So there's north here and north here. So these are like poles together. And what he's actually doing is using a compass. And notice that the orientation of the compass needle, depending on where he puts it, keeps changing. Now, if the compass was just by itself, it would point to the north. But notice that that angle keeps changing, and he's marking that angle on the paper. And as he goes around the two magnets, he's tracing the magnetic fields, or the space around the magnet in which that magnetic force is exerted. And so we get this particular pattern here. You also notice that the arrows, the orientation of the arrows is dependent upon the orientation of the white versus the red side of the magnet. Now, what he's going to do is he's going to take some iron filings and he's going to spread those iron filings on this paper on the magnets, and it should match up those lines, those magnetic field lines that he just got by placing the compass next to it. So we'll just wait a second here for as he's talking about exactly what I've just been talking about, and the magnetic field lines as they are joining in. Now, keep in mind that those lines do not come together in between the two magnets. And the reason they don't come together in between the two magnets is because we have two like poles, and like poles repel. All right, so like poles repel, and that's why those lines don't come together. So now when he takes these iron filings and he spreads them out, notice when they fall in the center, they're immediately pulled to one pole or the other, and they're pulled away from that area in between. It's that force of repulsion that is happening. And as he's spreading it out, you'll notice that the iron filings, they align themselves much like in the way of the marker that he had on the paper. You can see that pattern with the iron filings, but the real takeaway from this one is that force of repulsion that's in the middle. If he just keeps coating it with iron filings, eventually. Now, what I like to do when I do this demonstration in class, just what he did, I like to tap on it, and that kind of aligns them into that pattern magically. It's not magically, it's science, actually, because it's aligning with those magnetic forces, and each of those little pieces of iron filing are themselves becoming a magnet, because what happens is they are not magnets themselves, but they are magnetic materials. And when you place a magnetic material in the presence of a magnet, it becomes temporarily magnetized. So we have a couple different types of magnets. We have what's known as permanent magnets, which those north and south magnets on the picture, those are what we call permanent magnets. They all the time have magnetism. And then we have temporary magnets, which is basically a magnetic material that becomes magnetized when it's in the field of a magnet. One of the ways you can do this is if you have a magnet and you have a couple paper clips, take that paper clip and hang it off of the magnet, and then take another paper clip and it will attach itself to the first paper clip, because the first paper clip that's in the field of that magnet has itself become a magnet. Depending upon the strength of the magnet, depends on how many paper clips you're able to hold up. Now, in this example here, he's repeating the process with the compass and drawing the lines, but notice the connection between the south pole of the magnet on the left and the north pole of the magnet that's on the right. There is a connection that's there. And, when I take the iron filings and I spread that over there, I have a term that I like to say to kids, because a lot of people say that, they can feel it, but they haven't ever seen it. And I say this right here it's nothing could be more obvious. It is a force of attraction. It is what I call love. Right here in the middle of the screen, you see those iron filings connecting with one another. That's what love looks like. You have that force of attraction drawing them together. So now you've seen it. I would have liked to have shown it to you in person in class, but we have to go with what this guy is showing you. I do have the link to this video and the other video at the bottom of my slideshow if you want to watch them. You may or may not be able to understand this guy. But either way, you appreciate his knowledge in the video that he had here, because I was able to use it perfectly for this particular video. But this is the force of attraction, and compare this to the other one where there was nothing in between the two. Nothing at all in between the two. So now we're going to go back here to the notes. Electromagnetic induction. Now, this is okay. So, we were just talking about magnets, and that's just for general knowledge. But how do we use it? How do we use it in our lives? And electromagnetic induction is when we take a coil of wire. And it doesn't matter if you move the magnet inside the coil of wire or you move the coil of wire against the magnet. Either way, what's going to happen is you see the picture here where they're moving a magnet inside of coil wire, and it's causing this um, meter here to move. And so the reason that is because current is being induced or caused to flow in this line. So, and there's a relationship between that where the more coils there are, the more current there is. So notice here we have two loops. Now this is just a very simplistic drawing, but here we have two loops producing 1 amp. 4 loops produces 2 amps, right? And we increase the loops again, we get 3 amps. So we can increase the number of coils, and by doing that, we increase the number of amps that we produce, which is, keep in mind, amps is a measurement of current, which is the amount of electricity that is flowing through that coil. So if we increase the number of coils or number of loops, we increase the amount of current that flows through that particular wire. And again, like I was saying to you just a moment ago, the way this image is showing you, it doesn't matter if you move the magnet or you move the wire. As long as there's motion between the two, remember, all motion is relative. So as long as there's motion between the two, we can induce current that's flowing into the wire. Now, Michael Faraday, he was one of those brilliant scientists. And, around the turn of the century, in the early 1800s, what they would do is they would put on these shows for crowds. I guess it's one of the ways that they raise funds. I'm not really sure. About 50 years earlier, Benjamin Franklin, he did experiments with electricity, and he became pretty famous, both in the Americas. This was pre the revolution of 1776, but he became famous in the Americas, and he went to England, and he went to France, and he would put on these demonstrations for kings and royalty and wealthy people, and he became very, very famous for his demonstrations. Well, Michael Faraday, the story goes that he was doing the same thing. And what he did was he had this coil of wire, and he had a magnet, and he had it connected to a meter, kind of like the picture that does. And what he did was he had them separated. He had the coil of wire on one side, and the compass way over there, just connected by one wire, and he would move the magnet, and it would cause that wire to move. And most of the people in the crowd, they were astonished by it, and they're like, oh, wow. Well, the story goes that there was a young lady who was a bit skeptical of this. And basically she's like, Mr. Faraday, of what use is it? And to this, Michael Faraday became pretty indignant. And his famous reply to her was, lady, of what use is a newborn child? Now, what he meant by that is, think about when a child is born. Think about the potential for that child, what that child could become. That child could become a world leader and lead, have peace, a world peace that happens as a result. That child could be a doctor and come up with cures, maybe a cure for the coronavirus, maybe a vaccine for the coronavirus, right? That child, or a treatment, therapeutic medicine for the coronavirus. That child could become a great athlete. They could become a great artist, a great musician, or just an overall great person, that does great things and serves their community in a variety of different ways. And so we never know the potential. Certainly, the potential also means that child might not make it through childhood, or that child, might do some bad things in life, but the potential to do something good was there. And basically what Michael Faraday was saying was, to be honest with you, I really don't know what this means, but he believed that it was going to change the world. And guess what? It did. Just about everything that we touch and come in contact with today in 2020 is affected in one way or another by Faraday's law and this discovery that he had, because it is used in electromagnets. And electromagnets are used in a variety. Anything that involves with electricity is going to involve with an electromagnet. And just think about how that affects everything that we do. So a moving charge produces a magnetic field. The electric current produces a magnetic field, and same way. And so the magnetic field around a wire forms in concentric circles. So you see the picture here, the compass is around this wire. and they are aligned based on the magnetic field. Think about the magnetic field that we were talking earlier. When we run a charge or current through this wire, it produces a magnetic field around that wire. And it can even be just a regular wire that we have plugged in. Don't play around too much with electricity, but if you have a compass and you put it next to a wire that has electricity flowing through it, the compass will move as it moves next to that wire. Well, then what we can do is we can take that wire and we can coil it. And by coiling it, we concentrate that magnetic field in the middle of that coil. And that is the premise of an electromagnet. Um, and generators and motors are both working upon this principle. And basically, what we have with the generator is that we have a coil of wire. Now, this is a very simple drawing. Imagine in here all the windings. Remember the motors that we used in class, but all the windings that would have here inside of this magnet. And the thing is if we have mechanical input, in other words, we move it, we have some way to move it. Now, most generators are not hand crank generators. They might be steam powered generators, or we might have water that falls from a dam through a turbine that turns the generator. Or we might have a windmill. All those things basically are mechanical forms of energy or moving forms of energy that turn that coil of wire inside that magnet to produce electrical output. That's what a generator does. It converts mechanical energy into electrical energy. Motors are the exact opposite. Now, if you notice the picture here, I lost my place. If you notice the picture, it's very, very similar. It doesn't have the hand crank thing to it. But what we're doing is we connect it to a battery. And by sending electricity into that coil of wire, it now moves inside that magnetic field. Now, again, the top picture here is a very simplistic picture. The one down here is the insides of like one of those simple motors that we used in class earlier in the year. And it has many, many, many coils of wire, and it has these magnets, and it has these connections. But basically, the way an electric motor works is that we send electricity into the aperture that has the coil of wire and the magnet, and it produces mechanical motion. And then we take that mechanical motion and we use it for whatever it is that we're using that mechanical motion for. Whether it be to turn a fan blade to cool off, or to turn a blender to chop up your food, or to turn a drill bit, or whatever it is that we use to run a powered vehicle, or like a drone or something like that. All those things are examples of using electric motors. Now, the turbine is just simply the wheel that spins that is used to turn a generator. And that turbine could be a wind turbine, it could be a steam turbine, it could be a variety of other times. Think of a fan blade, that is a type of turbine that is used to power a generator. All right. And essentially, the motor effect is when the current is used to produce mechanical energy. And generator effect is when we use the mechanical energy to produce the electrical current. Now, we had talked about earlier in the year of direct current and alternating current. And in direct current, this doesn't work out this way. So alternating current, this is why alternating current and Tesla eventually won out over direct current and Edison. In the story that we had talked about earlier in the year, and that is that we can use transformers. There's transformers, there's transformers at substations, electricity, and there's this box that's out on the pole before it comes into your house. But basically, there's a ratio between this is the input and this is the output, right? And the number of loops of wire that's on the input versus the number of loops of wire that's on the output. Now, it turns out that if there's fewer on the input and more on the output, then it's what we call a step-up transformer that can increase the voltage. Whereas if the input has more wires and the output has less wires, then it's a step-down transformer. So what they do at the power plant is they use step-up transformers to step it up to very, very, very high voltage, can use that high voltage, that push on electrons, to move it for miles and miles and miles and miles, and then they step it down to a more safe voltage that we use in our homes and in our buildings in the way that we use that. So here's again some pictures of those transformers, and we have the power plant, we have the step-up transformer, goes through those high voltage transmission lines back down to a substation, step-down substation, to a transformer that looks like this on a pole that might be right outside your house, and then that goes directly into your house. Notice that in this scenario, the power plant is producing power at 12,000 volts. It steps up to 240,000 240,000 volts in these high voltage transmission lines, steps down to 8,000. So on the telephone poles, it's at 8,000 volts, and then it gets stepped down to 240 volts as it comes into your house. So, if ever there's a storm and there's a loose wire moving around, you don't want to touch it, because that's still 8,000 volts. It's still very, very high voltage. Remember, it's not voltage that kills, it's current that kills, but we don't know what the resistance is going to be. So you have to be very, very careful of that. So that is our lesson in magnetism and electromagnetism for today.